connections first is any questions? Connections? No problem? Connections? Okay. Okay, now we start the second part of this afternoon session. Your opponent please propose the problem for the reporter. 1 minute. You have 1 minute.
We would like to challenge problem number 2, air muscle.
Problem number 2.
We accept.
Okay, problem number 2. Accepted by the reporter. 5 minutes preparation time for the reporter. Problem number 2. Please write down names for each team's presenters. On the bracket. Okay, the reporter has 12 minutes to present his work.
Hello everyone, this is the reporter from Mingdao Mayan, and my topic today is air mussel. So this is our problem statement. Place a balloon inside a cylindrical net as is sometimes used to wrap garlic and inflate it. The net will expand and shorten. Investigate the properties of such a mussel. And our main focuses are the generated force and pressure. So this is my outline. And this is my demonstration video. As we said, we will inflate the balloon and our air mussel model will shorten and expand. So this is the phenomenon observation of our experiment, where, as we just said, it will, after the inflation, it will be shorter and it will first expand and become shorter. And this will also happen when the real mussel needs strength. So we have done a preliminary experiment first because we want to know the pressure inside the syringe in our mussel model. So we use a force accelerometer to push the syringe, and as we know, the pressure equals the force divided by area A, so we can know the pressure inside our model. So these are the graphs of our preliminary experiment. So before the experiment, we thought that PV will be constant, which made up our theoretical line. But we observed that the result isn't PV equals constant. And so using this graph, we can know the pressure inside our model. And next is our theoretical part. So first, we're going to divide the direction into two directions. One is radial direction, and the other is the axial direction. So we can have an equation of the radial direction over here. So it will be mostly about the pressure that's acting on the side of our cylinder, and also the radial stress and fiber tension. And the other equation is about the axial direction, and it is mostly about the force F that we're measuring and the pressure that's acting on this bottom side of the cylinder, and the axial stress and also fiber tension. So we're going to solve the system of equations, and we can get the final result of F, and it looks like this. And by the way, the pressure P in our experiment is the P minus P0, which P0 represents when the balloon touches the fiber net, the pressure when the balloon touches the fiber net. And because we want to turn a trigonometric function into the value we can measure, so we will turn the cylinder into this triangle over here. And based on the geometric relationship of its shape, we can know the exact value of tangent theta, and we can put it into here. So at last, the simplified expression for the axial force F will become like this. And next is our experimental setup. So we have a syringe, a flexible tube that connects the model and the syringe, and the model made of fiber net and balloon, and also a force accelerometer. And we have used three kinds of fiber meshes, and also two kinds of different model using two kinds of balloon, which are cylindrical balloon and ball-shaped balloon. And we're going to emphasize the force that we're measuring. So because our model will shorten, so it will pull on the rope, and our force accelerometer will know how much force it is pulling on it. So next is the experimental data. So the first experiment we're doing is investigating the effect of internal balloon pressure P on the generated tensile force F. So there is a video of our graph, and it will look like this, because we will first push the air into the syringe, into the model, and we will pull the air back to the syringe. And this will cause two curves in our graph, which are pressurization curve, which is the blue line, and the depressurization curve, which is the orange line. So we will describe it more detail. We can see that the pressurization and depressurization curves are slightly different. And also, before the pressure P reaches approximately 1.38 atm, there's no force. And the reason there's no force is because the balloon haven't touched the fiber net yet. And also, there's a maximum value in our experiment. It's because if we inflate the balloon too much, it will damage our model. And there's another experiment of us using cylindrical balloon, and we're testing different kinds of fiber mesh on our cylindrical balloon. So these are three graphs of our experiment. So I will describe it from the shortest diameter to the longest diameter. When we're using the shortest diameter, we can see that the two curves are very similar. And when we're using the medium one, we can see that the depressurization curve will be slightly lower. And when we're using the longest diameter, we can see that the two curves are more different. So as a result, we can say when we're using a fiber mesh with a longer diameter, the depressurization curve will be significantly lower than a pressurization curve. And next is the experiment of us using ball-shaped balloon, and we're also using 3 kinds of different fiber meshes. So we will also have 3 kinds of graph, and on the left is the shortest diameter, and on the right will be the longest. And we can also observe that when we're using a fiber mesh with a longer diameter, the depressurization curve will be significantly lower than the pressurization curve. And the next part is the discussion part. So the first main point in our discussion is the comparison between a cylindrical and ball-shaped balloon. So when we're using as we can see, when we're using ball-shaped balloon, the depressurization curve will be significantly lower. And also, it will generate F as at a smaller value of P. As you can see, this is the graph of using the cylindrical balloon, and this is the graph of using ball-shaped balloon. And it generates force at 1.38 ATM, and it generates force at 1.17 ATM. So the ball-shaped balloon will generate force faster. And we also observe these 2 phenomena when we're using the medium diameter. And we can also see this when we're using the longest diameter. The next, we also have an observation is that when we're using the same type of fiber, which is the thinnest, medium, and the thickest, the model using ball-shaped balloon will generate more force per pressure increase, and it is also as known as the slope of our graph. So the gray line over here represents the line, the experimental line that we're using ball-shaped balloon, and the blue line are the line we're using cylindrical balloon. So we can see that in three fiber meshes, the slope of using the ball-shaped balloon is always larger than the slope of using cylindrical balloon. The next is the discussion of muscle energy consumption. Because according to the first law of thermodynamics, the change in internal energy of the system comes from work or heat. And when we push the syringe, we have the exact value of work. So what is left will only be the dissipated heat. So we want to calculate the exact value of energy consumption, so we change the graph to the relationship of force and pressure into the relationship of force and delta x, which is known as L minus L0. So we split the graph into 2 graphs, so we can get a graph of the applied pressure and then the other graph of release pressure. And as we know, the area under the curve will be the work we have done. So if we minus those 2, we can get the exact value of energy consumption. So these are the graphs of our experiment, and on the left it is using cylindrical balloon, and on the right is using ball-shaped balloon. And these are the graphs when we're using the thinnest diameter, and the medium diameter, and the thickest diameter. And we have organized them into one graph to make it easier to see. Since we want to know the value of energy consumption per Newton generated, we divide the energy consumption by the force it had generated, and we can get those values over here. So if we compare down, we can see that when we're using a thicker fiber mesh, there will be greater energy consumption. And also, when we compare it right, we can see when we're using ball-shaped balloon, there will also be greater energy consumption. And next is a compare between different diameter of the fiber. So when this is a graph where we're all using cylindrical balloon, and this is a graph where we're all using ball-shaped balloon. So as we can see, when we're using the same balloon, the thicker fiber we're using, it will generate more force per pressure increased. The gray line is for the thickest diameter, and the orange line is for the medium, and the blue line is for the thinnest. So as you can see, the slope is always biggest on the thickest and the medium, and then at last it will be the thinnest. So we can, as a result, we can say that it will generate more force per pressure increase. And at last, we're going to compare our theoretical data and experimental data. So we can see that the 2 lines are very similar over here. We divide the graph into 2 graphs, which are applied pressure and release pressure. And the reason we will also have two theoretical lines in one set of experiment is because that even though the pressure is same, the volume will not be the same during the pressurization and depressurization. And the volume is also known made of L and R over here. So because the L and R are not same, the theoretical line, well, we will have two theoretical lines. And I also have the theoretical line of other set of our experiments, and if you're interested in it, we can discuss it in the discussion part. And at last, it is conclusion. So as you can see, the balloon using the model using cylindrical balloon will consume less energy, but it will need higher pressure to generate force. And also, the model that using ball-shaped balloon will generate force at a lower pressure, and it also generates more force per pressure increase, but it will consume more energy. At last, the model using the same balloon but fiber mesh of longer diameters, it will generate more force per pressure increase, but it will consume more energy. So this is the end of my presentation, and thank you for your attention.
2 minutes for the
Did the opponent pre-stretch the net or balloon before placing the balloon inside the net?
You say, do we?
Pre-stretch the net.
We didn't stretch it. We didn't use hand to stretch it, but we inflated and deflated.
So you did or did you not?
We did.
Okay.
We didn't use hand, but we inflated.
I get your point. Did you only visually confirm the cylindrical shape of your balloon or the circle balloon throughout your experiment? So you said you conducted the experiments using the cylindrical shaped balloon and a circle shaped balloon. Did you only visually confirm those shapes?
Visually.
Confirm those shapes.
Oh, we have a.
A short answer.
Only by shape. Or
Visually,
do
yes.
we measure it?
Measure and
We did
confirm.
measure. We did measure.
Okay. Did you assume the balloon will maintain in the same shape throughout your experiments?
Sorry again.
Did you assume the balloon will maintain the same shape throughout your experiments?
Maintain it. Always be the same shape.
Yes. In the same sort of shape, like circle or cylindrical. Short answer, please.
Yes.
Did you consider the air pressure and temperature inside the balloon to be uniform while pumping?
Temperature?
Yes, air pressure and temperature.
Air pressure and temperature.
Yes.
But air pressure is the.
I'm sorry. Then temperature.
Oh, only temperature.
Yes.
We didn't measure it, but we considered it in our experiment.
In the same. The temperature is the same.
No.
No. Okay. Did you measure the maximum shortening percentage of the net?
Maximum percentage.
Or did you measure the maximum shortening of the net?
Oh, we didn't have the data over here.
Did you measure the volume of air? Did you ensure that there were no leaks in your balloon inflation system?
Yes.
Okay. How often did you change your
Time
balloon?
is up. 3 minutes preparation time for the opponent. has a maximum of 4 minutes to present his argument, followed by a discussion between opponent and the opponent, for a total of 14 minutes.
Honorable juries and fellow competitors, I am the opponent from Team Excel here, and for today, I'll be opposing problem number 2, air muscle. The problem statement reads, attach a balloon inside a cylindrical net, as is sometimes used to wrap garlic, and inflate it. The net will expand and shorten. Investigate the properties of such a muscle. Today, we'll be mainly focusing on the relation between the expansion of the balloon and shortening of the net. And for the second one, how will parameters affect the properties of the muscle? And next is an outline for the report. For his theory, he used the force analysis to describe his phenomena and setup. And he used a PV equals constant in the original state, but he found out laterwards that it wasn't a PV equals constant. And he also gave an equation of the radial direction, and also he gave an equation for the axial direction for the net and balloon. And for experiment and analysis, one of his parameters was the length of the cylindrical net, and for the size of the balloon is something that we want to talk about. Size of the balloon is divided into a circle and cylindrical shape. And for the 2 and 3 are the same. And for controversy and deviations, the opponent believes that there might be elastic fatigue of the balloon and net when the reporter conducted experiments. And the temperature differences could also cause some deviations to his theory or to his experiments. Next, I'll be talking about the strong and weak points of the reporter. The reporter provided a clear observation video of how he conducted the experiment and showed the phenomenon well. However, he failed to optimize the precision and accuracy, but he did explain the phenomenon of the air muscle very well. However, he failed to explain the cause of some deviations. And he also provided lots of error bars in his graphs. However, he had a lack of parameters for experiments. And he also compared the experimental data with the theory he drew. However, there was some lack of theory line in some graphs. And the opponent didn't measure the temperature, which the opponent thinks is quite a major factor in this problem. Next, I'll be talking about the points that we want to discuss later in our discussion. For experiment, we'll like to ensure about the initial conditions before he conducted every single experiment. We'll also like to question about the elastic fatigue problems the reporter might have faced when he conducted experiments. Also, we'll also talk about the air leakage and how he ensured that there was no air leakage in the system. For data collecting, we'd like to understand how the reporter ensured the pressure of how did the reporter measure the pressure of the system. We also like to know how the reporter measured the volume of air. We also like to ask about the measure of temperature and the shortening of length. And for the theory, we'll like to talk about the force analysis, and we'll also like to focus a lot on the surface tension of the balloon and the net. And for the properties of the muscle, which is part of the problem statement, so the opponent thinks is important, is how much the weight of the muscle, how much weight can the muscle lift, and also the agility of the muscle. And most important, the energy efficiency of muscle. The opponent believes that the reporter should have a standard for the energy efficiency of muscle, which the opponent will explain later on. And for the parameters, we'll discuss about the length of the net, which could cause some deviations. And we also like to discuss about how this parameter affects the impact on energy efficiency. We'll also like to talk about the different sizes of balloons. For example, like previously we asked the reporter how did he ensure the shape of the balloon. And also, this could also cause some deviations, and again, it will also impact on energy efficiency. So we would like to start our discussion. So first, could you please go to page 2?
Page 2.
Yes. Never mind. So from page 2, in the problem statement it reads, attach a problem statement. Place a balloon inside a cylindrical net as is sometimes to wrap garlic. However, the reporter conducted experiments using a fiber net. Am I correct?
It is made of fiber. A cylindrical net is made of fiber.
Yes,
so
but however, do you not think that as a cylindrical net, as sometimes used to wrap garlic, should look something like this, as we would sometimes see in Taiwanese supermarkets?
As you can see, on the
Wouldn't not using the cylindrical net stated in the problem statement affect the outcome of experiments?
can you use easier words? Sorry.
So if you didn't use your cylindrical net, as sometimes you wrap garlic, wouldn't it affect the result of your experiment? So when using this kind of net and the fiber net, wouldn't it cause some differences?
Because as the main, problem statement said, that it's mainly using the cylindrical net, and this is just a kind of also a cylindrical net, and it can also use to.
Okay. The opponent gets your point. However, he suggests a reporter to conduct some experiments using the net that the problem statement would advise us next time.
Oh,
So,
okay. That's
And-
the suggestion.
Okay. So we would also like to ask about. Could you turn to your page when you have a theory line and your data analysis?
Okay. Sorry, it is.
Turn to your page where you have the theory line.
Here.
Excuse me. Which one is your theory line?
Also, we have it over here. So
Oh,
the
okay. Yes.
white one is the theory line, and the blue one will be
Or
our.
can you go back
data.
two more?
Two more.
Yes. More. Wait.
Yes.
There.
Uh,
Like go backwards. Go backwards.
backward. Oh.
No, backwards. Sorry. The opponent remembers that there is a.
I don't get it.
Yes. This.
Oh, this one?
Yeah.
Oh, okay.
Okay. So this is your theory. Am I correct?
This is my theory line, and
Yeah.
this is my experimental data.
Okay. So could the reporter please tell us why is there such a difference between your experiment and the theory? Could you explain the deviation?
That's because in our theory we think that PV will be constant, but actually it's not, because the temperature of it will it will not be constant.
Well,
the temperature will
Did you
change.
eventually find a fitting line to match your experimental data, in which PD is not a constant? Did you find a specific number, or did you?
Oh, the correction?
Yes, the correction.
Oh, we didn't have the theory correction.
Yeah, so the opponent suggests that maybe the reporter would consider using error analysis next time, so you could fit your theory line to your experimental data next time. Okay. So, so regarding to your experimental data, could you turn to a page where you matched your maximum force?
Maximum force.
Yes.
Oh,
I remember that you mentioned about the maximum
Yes.
force.
Here.
So, in this place, this is the maximum value. So, if you theoretically, if you pump more air into the balloon, it would explode. Am I correct?
It's not about the theory. It is just limited by our model, because if it is a little bit easy to broke. Not very easy, but if we inflate it too much, it will just break through.
So what is the largest force that your muscle could provide before it breaks? The highest number you have analyzed.
We have it at the over here. Sorry, I don't to have it right away. Over here.
Okay.
No, wait, sorry.
Okay, never mind.
Okay.
We get your point.
Okay.
And so, did you ensure your balloon will not experience elastic fatigue throughout your experiments?
No.
So it won't experience elastic fatigue.
No, it won't, because we have already inflated and deflated many times,
Okay.
and due to the malevolent effects, when we do this many times after, it will go into a stable state, and it will not really have the stress softening of the balloon.
Okay. However, you said that after you conduct many experiments, you will go into a state where it will become a softening and it won't cause any elastic fatigue. But isn't that the state when it already has experienced elastic fatigue?
You mean from the start to the
Yes.
end?
If you conduct your experiments to a point where when you pump the same amount of air into the balloon and it will just generate the same amount of air, does that mean that the elasticity has already occurred?
It has already happened and it won't happen in our experiment.
Yes, however,
Yeah.
don't you think that, or maybe you could try to conduct more experiments before the last fatigue and after last fatigue, so it could show a well-rounded experiment for your experimental data. That's what the opponent just suggested. Okay. So, could you please draw, Juries, please use the blackboard. Okay. Could you please analyze the forces that happen in your system?
Forces, can use my PowerPoint because I have the.
Oh yeah, sure.
So it is in my theory part, and I have two directions as I mentioned in my presentation. So the first direction will be about the radial direction over here, and it is you can think it like this. We will divide it into half, and we will divide these two into the one that is pushing upward and the one that is pulling downward.
So we noticed that we lost all these forces inside your force analysis. So,
yes.
But did the reporter ever consider about the friction between the muscle, between the balloon and the cylindrical net?
Yes, we have considered it in our experiment, and it is so it caused the energy consumption of our experimental data.
So can you quantify the friction?
We have the work that it have gone.
We got your point. Thank you.
Yeah.
All right. So does the reporter believe that the surface tension of the balloon will be the same around the balloon?
We assume it. Yeah, we assume it right.
You assume that the surface tension will be the same around the balloon.
When we're using ball-shaped balloon, but not cylindrical balloon. Because the way that ball-shaped balloon expands, it is like this.
Do you have an observation video showing the experiment for your ball-shaped balloon?
No. We don't have one.
Then the opponent suggests that you could probably provide an observation video to ensure the validity of your experiment, so that we can all understand that it actually is first of all, it's actually is a ball-shaped balloon, or it's actually a cylindrical shape, or it won't cause any deviations such as the surface tension is not the same.
Okay.
And okay, so we would like to mainly focusing about the energy efficiency of the muscle, meaning one of the properties of the muscle. So, did you define the energy efficiency of the muscle?
Yeah. So what is it?
So the definition for energy efficiency. So I would like to give an example. So, for example, the air muscle is an analogy of a real muscle. So if you're considering if you have set a standard for a good muscle, so you would probably conduct 4 newtons of force into your muscle, and it would release 4 newtons of force.
We have it as a result, and it is.
But did you set a standard for like a good air muscle, or a good energy efficiency?
So we can only say that it will generate more force per pressure increase, but we cannot say it is just good by it, because it will have the model that have the model that will generate more force per pressure increase. It will also have more energy consumption. So we also have to think about that.
The opponent suggests that maybe the reporter can actually set a standard for the energy efficiency, because maybe later on, if you try to change any parameters, or if you pump, like for example, if you pump more air into the balloon, you could have like a clear standard to see if this is a good air muscle or not, which is one of the properties of the muscle. So that's just what the opponent suggests. You can set a standard for the energy efficiency.
Thank you.
Opponent has 1 minute to summarize.
We would like to now summarize our discussion. So first, we talked about the different material for the net. We discussed about the normal garland net as shown over here, and also discussed about the fiber net that the opponent conducted. And the reporter didn't exactly correct the theory line after finding out the PV will not be a constant. So the opponent suggests that next time he would conduct error analysis to fit his experimental data. And the reporter didn't measure the biggest pressure before the balloon explode. So he has some deviations that he didn't explain, and the opponent suggests that the reporter can explain it later on. And the opponent thinks that elastic fatigue will cause some deviations to the experiment, and also the reporter did consider the friction in the experiment, and we both agreed on that. And the reporter assumed that the surface tension will be around the balloon, but didn't show the observation video about it, which could cause some validity questions. So the reporter suggests to do so. Thank you.
Question time for the reviewer, 3 minutes.
Okay, first question for both opponent and reporter. What is a good air muscle?
Okay, so the opponent suggests to set a standard for a good air muscle. So maybe, for example, if you apply maybe 4 newtons of force into the muscle, and it could generate maybe even more force, or maybe approximately the same force, we would consider it a good muscle.
I think that the muscle with lower energy consumption will be the muscle for, but it needs to depend on which kind of thing that you're going to use the muscle. Because one is that in our experiment we can see that the muscle that can generate more force per pressure increase will be the ball-shaped balloon, but at the same time it consumes more energy, so it will have more energy loss. So it depends on what kind of way you're going to use your muscle. So this is a question that I cannot answer directly.
Okay, thank you. Okay. The balloon shape. Is the balloon shape will cause something effect to the ATMs or PSI?
Because we measure it by the preliminary experiment that we have mentioned, so I don't really know what you're talking about.
Could you rephrase your question?
Okay. Well, the different shapes of the balloon cause something effect to the air pressure.
Within the balloon,
Yes.
we believe that it could cause some differences. Yes.
How did the temperature affect to the system?
Well, so for example, if the temperature is not remaining as a constant, then it's not like so it's not an isothermal expansion. So temperature would cause the how you analyze the muscle and how you analyze the temperature inside the balloon, and it would affect your analyzation.
The temperature of our experiment, it will affect the muscle energy consumption. It is because when we inflate the balloon, the temperature will go up. But the temperature is always want to become the same with the place that we're in. So it makes our energy consumption over here in our experiment.
You have a F2D graph about the
Okay, time is up. 2 minutes preparation time for the reviewer. Okay, the review of this is the form for total 4 minutes.
Okay, first problem statement of problem 2. Place a balloon inside a cylindrical net as is sometimes used to rub garlic and inflate it. The net will expand and shorten, investigating the property of such a muscle. Summary of the report. Theory and explanation. Report focused about the pressure that put inside the muscle and have 4 stages of the experiment, step by step, to get the final result. As different the diameter of the net is, the result could become lower. Compare the balloon shape to get different result. About the experiment setup, net, syringe, 2 different types of balloon, and 3 different diameter net. Reporter first pros talk about deeply into the theory, talk about a PowerPoint clearly. Using tracker in the video version. About the cons. There's only 2 types of balloon in the experiment. Didn't discuss the function deeply. Summary of the opponent. Opponent have mentioned 2 of the theory about the force analyzed and surface tension. In the experiment, the length of the cylinder, size of the balloon and different shape of the balloon, and focus on the material or geometric, and impact of the energy infection. The opponent pros focus on the temperature and the air pressure, which is detailed of the experiment. Ask questions on the some important detail that opponent didn't notice, such as the temperature. Have a chart of the point to be discussed to clear the point. And I think opponent gave the suggestion to every detail. Opponent didn't check. Cons didn't ask deeply about the data analyzed. Discussion about the experiment. Opponent did ask about why there is such a difference between the theory and the experiment. And reporter say they have wrong thought about the experiment, and opponent gave a really good suggestion. That's all.
The reporter has 2 minutes for the closing remarks.
Okay, so both opponents and reviewers have good points, but there are some concluding remarks. What we want to do is to do some points to clarify. So, the fiber net we're using is still cylindrical. It is just little difference in the material, so our experiment setup still meets the problem statements requirement over here to answer the opponents. And the fiber net is stretched many times to avoid elastic fatigue. So we did consider this, and that might have an impact on the experimental data. So we have already done the things that can avoid this. Okay. So also there is a heat exchange in the process. So it is not as either adiabatic expansion or isothermal expansion. So what I mean is that I did consider it in our experiment, and we did consider the temperature change, and this caused the energy consumption, as I mentioned in my presentation. And at last, according to the first law of thermodynamics, we will only have two kinds of thing after we applied force on it. It will only be the work and heat. And because when we push on our syringe and it pushed back, it will have our work return. So the thing that it didn't return, it will be the heat that it had already that it is gone. So the heat will be our energy consumption over here. And this is the end of my concluding remarks, and thank you for your attention.
Questions from jurors? Questions? Go ahead.
I have a question for you guys. How you define the good muscle? For you,
Can I have a longer this one? Because if we need force immediately, a good muscle will be like a muscle that can generate force if we only give a little bit force and it can have a big force generated. So this will be a good muscle when we need force immediately. But in the other situation, a good muscle just perhaps like the muscle that needs that needs to work for a long time. So this kind of when we need to use a muscle this way, the muscle with lower energy consumption will be more ideal if we want to use the muscle this way. So the good or bad of the muscle, it is think of that the way that we want to use the muscle.
Okay, just like the reporter says, when you add air pressure or liquid pressure into the muscle, and whether it can turn into forces accurately.
So we agree with the reporter that there are different situations when you want a different good muscle. So there could be situations where you want the energy consumption to be minimum, and there could be situations where you want instant force that generates from the muscle. And for our example here, we were mainly focusing on like the instant kind of muscle. However, the opponent agrees with the reporter that there could be different definitions for a good muscle according to different needs.
Okay, thank you.
Just one more question. It's a follow-up action. First, can you consider two extremes? One is the adiabatic process, that means you inject the rate very fast, and the other extreme is you just put the piston very, very slow, such that it is isothermal. So which is a high efficiency, powerless motion, and what is a high power but low efficiency process?
You mean by what is
Injection rate. For example, if you inject the gas very fast, you can consider it is an adiabatic process, right?
Oh, we didn't do the experiment of pushing very fast.
Just confirm your thought.
Oh, confirm my thought. If we do it very fast, I think that because it will be I forget that the specific word, but the heat of it will not go out so fast. So we can see that we can maybe observe that PV will be very close to constant. So as we can just like the experimental data that we see. So if the PV will be almost constant when we push it at the same thing, when we push it at the same length, the pressure will go up more. So it will maybe generate more force.
So as the speed of pressure put inside the muscle, I think the force will get bigger.
Okay. So the definition for adiabatic expansion is when you pump, when the expansion happens really fast, it won't have any heat exchanges with the outside area. So with that being said, if there are no heat exchanges at all, then the adiabatic expansion would theoretically cause a better efficiency for the muscle.
And on the other extreme, if it is an isothermal process, then what is the case?
If it's an isothermal process, then theoretically you would pump the air slower, because if you pump it really fast, you would cause the temperature to rise. So, but if you pump it more slowly, it would let the temperature mostly remain as a constant. So in that case, it would have not such as a high efficiency, we believe.
More questions? Thank you. showing this book, okay. For the reporter. We have 6, 7, 7, 6, and 9. For the opponent, we have 7, 7, 8, 7, and 8. For the reviewer, we have 5, 4, 5, 4, and 6. Okay, this concludes our second part of this afternoon session. Okay, we can take a break now. Should we take a 10 or 15 minutes break? Which one do you prefer? 10? 15? 15. Okay, let's take a 15 minutes break.